Hi everyone, and welcome to our Physics Daily Booster. This is number 18 and the final one in our Paper 2 series. Even though this is not on the advanced information for either the foundation or the higher tier physics, as we know from previous experience, that doesn't mean that questions will not occur on this topic. So worth going over it just in case. This is the mark that makes the difference between one grade and another for you. What we're going to do then is have a little look at the last bit of P8 today. So first of all, we need to understand about radiation in terms of generally space and how this applies to things like stars. If we go to basics, all objects emit electromagnetic radiation. Warm objects are going to emit infrared radiation, and we can detect that with a thermal imaging camera. Think back to some of the work we've done in our previous physics work. Now, the type of radiation emitted is going to depend on the temperature of the object. And what we actually find is that objects at different temperatures look different colours. So if we think about what we consider to be a hot object, like if you heat up some metal, then it's going to start to glow red first of all. Now, actually, that's relatively cool in the grand scheme of things. Don't touch it still, it's going to burn you, but still, that is a cooler part. The yellow bit on the metal, if we've kept heating it, is going to be hot, and if we manage to get it to a bluish white colour, that's the hottest. So just by looking at the different colours there, we can work out the temperature of the object. So, in terms of the radiation then being emitted by our objects, the hotter objects will emit more radiation of higher frequency and shorter wavelength, and they emit less radiation of the lower frequency, longer wavelength. Now, what that means is, and I've given you a little picture down here to help you understand this. So we've got the warm object on top, red hot object in the middle, white hot object at the bottom there. So if we have a little look, what we can see is the frequency is increasing further towards the right. So what we said, hotter objects emit more radiation of a higher frequency. If we have a look, the white hot object, the one we said was the hottest of these, that bar is extending right the way towards the ultraviolet range, which tells us that we've got higher frequency radiation. If you only look at the warm object on that top bar there, you can see that that's actually got a much lower frequency. So why does this matter? How does this apply to space of all things? Well, we can't travel to another star to actually take measurements up close. Doesn't work, takes a really long time, we don't have the technology to do that. So we have to rely on other methods to work out what these things actually are made of, what temperature they are, etc. And what we actually do in order to work out the temperature of our stars is we can analyse the light that is given off by them. And what we can then do is we can plot a little graph like we can see in this bottom right corner here, which is showing us the frequency and the intensity of the radiation that we get. So higher frequencies are further towards the left of the graph in this case. So what we can see is that purple line, the one that goes up to the highest peak, then this is our hottest star. So remember, the frequency is highest towards the left. So because we've got that high peak on that high frequency, we know it is a hotter object than, say, the red line, because that only has a very low peak in terms of the high frequencies there. So just by looking at what radiation is being emitted by those stars in far-flung reaches of the universe, we can actually work out the approximate temperatures of them, because those hot stars have higher frequencies at higher intensities. If we consider how radiation affects the temperature of an object then, if our object is emitting the same amount of radiation as it absorbs, we'll have a constant temperature, because obviously whatever we're absorbing, we are also emitting. Hopefully that's logical. If we absorb more radiation than we emit, we are going to see a temperature increase. Whereas if we see more radiation emitted than absorbed, it's going to have a temperature decrease, it cools down. Again, I'm hoping that's relatively logical for us. So again, we've just discussed random facts about radiation. How does it apply to space? If we go back to what we've said previously in physics, think back to what we've said in terms of climate change, etc. Then we have got the sun. Now the sun is emitting radiation into space, and some of that radiation is going to reach us here on planet Earth. So what happens is Earth is going to absorb the radiation from the sun, and it then emits radiation into space. Because remember, the Earth is obviously an object with a temperature, therefore it will emit radiation too. In terms of our atmosphere, what we find is some radiation passes straight through the atmosphere and off into space it goes. Other radiation is going to be reflected back to Earth by the atmosphere. One of the key things that determines how much of that radiation is going to be sent back to the surface of the Earth is the concentration of the greenhouse gases, carbon dioxide, methane, and water vapour. If we have a greater concentration of greenhouse gases, then we're going to have a greater amount of radiation directed back towards the surface of the Earth, and that leads to the enhanced greenhouse effect and therefore global warming. The very final bit of P8 is all about the structure of the Earth, so big overlap with those of you that do geography here. Nice little reminder of some of your Key Stage 3 work to start. We have 4 of these internal divisions of planet Earth: the crust, the mantle, the outer core, and the inner core. So obviously the crust is the bit right the way around the outside, mantle is inside that, then we get to the outer core, and finally the inner core in the very centre. Now, in terms of how we study the Earth, we can't just get a big drill and just drill down to look and see what's in the middle there. 2 key reasons. One, it's too deep. The planet is really quite big. And secondly, it's far too hot. Anything we tried to use to drill down there would literally melt. So it's not going to work for those 2 key reasons. Therefore, how do we know that we've got these 4 different divisions that make up the structure of the Earth? And the answer is earthquakes. Hopefully we know that earthquakes produce seismic waves, and those seismic waves we can actually detect on a device called a seismometer. So basically it's kind of like a little pen on a little arm, but as the Earth shakes, it shakes and draws a little line. Very simple version. Obviously these days we have computers that do this for us. But those seismometers are actually going to create a seismogram, the thing that we're creating, the picture if you like, and that's going to record 2 key things. Firstly, the point of arrival, and secondly, the intensity of our 2 types of seismic wave. P waves or primary waves, and S waves or the secondary waves. So by looking at that seismogram, we can see when did the S wave arrive, when did the P wave arrive, and how much of them was actually detected. So what we then do is we are going to have a look, not just at one seismometer, but at many. So what we've got, our little picture on this side, is just giving us a little bit of an idea of how all this ties together. We've got our epicenter of the earthquake on this left-hand side of planet Earth. So the epicenter of the earthquake is basically where it originates from. Now, at that point, we are going to be generating both S waves and P waves. And if we have our little seismometer anywhere near the epicenter, so here or here, for example, around here, we are going to detect both S waves and P waves. However, if we have our seismometers at different locations of the Earth, then we don't detect everything. Now, we would actually have these regions called shadow zones. So in our shadow zones, what we'd actually find is there are going to be some regions where we are not going to detect either S waves or P waves or either of them. And based on which waves we detect where, we can then put together information about the structure of the Earth. The reason for that is down to those individual waves and their features. When we're talking about P waves, these are longitudinal waves and they can travel through both solids and liquids. Whereas the S waves are transverse waves and they can only travel through the solids. So they cannot travel through a liquid. As a result of studying all these different seismographs from different seismometers across the surface of the Earth from different earthquakes, then we came up with this idea that actually the core must be liquid, because there were regions of the Earth that were obviously different location to where the epicenter of the earthquake was, that we were able to detect the P waves but no S waves. So that tells us that if the P waves can travel but S waves can't, there's got to be something liquid between those 2 points. We then go a little bit further from 1914 to 1936, and further analysis of the P waves allowed us to work out that actually the very centre is a solid. So rather than just having the core, which was liquid, we then divided it up into the outer core and the inner core. So the outer core we know is a liquid, the inner core is a solid. So that gives us our 4 divisions of the Earth now, and that's how we worked out just by using those seismic waves. And in fact, through further studies, we've also worked out the sizes of the inner and outer core as well. But all of that done through seismic waves, none of it by actually drilling down and looking at it directly. Obviously, if there are any bits from today's Daily Booster that you want to go over in a bit more detail, you can use the P8 playlist on the channel, you can use your revision guides, and of course do have a look at some of the past exam papers. Don't forget to join us tomorrow for the live stream for Physics Paper 2, which will be starting at 6 PM. So hopefully see you tomorrow for the live stream for our final paper of the exam season.